Kyle, I have a request to explain the logic in 1.442. Excellent question. So let's go ahead and talk about it. Now, you might get it correct by guessing since it's a multiple choice question, but this is a very good question that could be on a test too. So we need to understand the concept. It's asking when is the sine of 3x equal to the square root of 3 over 2? And of course, it gives us the domain of the first revolution of the unit circle from 0 to 2 pi. Now, keep in mind, if x is between 0 and 2 pi, the angle that we have inside the sine function is 3x. So 3x could be any angle between 0 and 6 pi, multiplying 2 pi by 3 to get to the 6 pi. So the angles that I need to look for are in the first three revolutions of the unit circle. Now, in the first revolution of the unit circle, the angles that are going to satisfy that criteria are when the angle in quadrant 1 gives you a y value of the square root of 3 over 2. Remember, you only need to know when y is three different values in there, when it's 0, when it's 0.5, when it's the square root of 2 over 2, and when it's the square root of 3 over 2. Well, I guess 4 when it's 1. But whenever the sine function is 1/2, the angle is pi over 6. When the sine function is the square root of 2 over 2, the angle is pi over 4. Whenever the sine function is the square root of 3 over 2, it's pi over 3. Anytime that the pi is over 3, the sine function is going to be far away from the origin. In this case, a 60-degree angle or pi over 3 radians. Now, because of that, I know this angle over here has to be pi over 3 as well. And we know that this would be pi, which is the same thing as 3 pi over 3. Subtract pi over 3 from that, you'd get 2 pi over 3. Those are the only two angles in the first revolution of the unit circle that the sine function could ever be equal to the square root of 3 over 2. Nowhere else can the y component be square root of 3 over 2 or 0.866 as a decimal. So whenever I think about this, I just think this is asking me when is the y component of the unit circle going up 86.6% of the way from 0 to 1, approximately right here, and these are my two angles that satisfy that. Now, since I have to think of three revolutions, we can say, well, those are the only answers in the first revolution, but I could go on around and say, well, as long as that angle 3x gave me a coterminal angle to this one by rotating around another 2 pi radians, and in that case, you'd say, well, that angle would be pi over 3 plus 2 pi, which is pi over 3 plus 6 pi over 3. I'd get to 7 pi over 3. And then another coterminal angle, if I rotate it around another 2 pi radians, add another 6 pi over 3, it would take you to 13 pi over 3. So I would have all of these values for that first angle in quadrant 1, but of course, any coterminal angles within the first three revolutions to the angle 2 pi is also going to be correct. Similarly, you'll just add 2 pi radians or 6 pi over 3 to each other solution. So you'd say, well, it's going to be 8 pi over 3 or 14 pi over 3. Oop, 14 pi over 3. Now, that's what the entire angle 3x would have to equal. So I can say, well, all right, if 3x is equal to, and I'll go in order, pi over 3, 2 pi over 3. My next one would be 7 pi over 3, then 8 pi over 3. It's 13 pi over 3, and finally 14 pi over 3. So if I get that 3x is equal to all of those angles, then when I divide by 3, x is just going to be pi over 9, 2 pi over 9, 7 pi over 9, 8 pi over 9. None of these are simplifying any, since none are multiples of 3 in the numerator. 13 pi over 9, and finally 14 pi over 9. That should be the final answer. Now, I promise you could plug any of these angles in for x in that original function, and it's going to satisfy it, because we know that, for example, the sine of pi over 3 is equal to the square root of 3 over 2. Well, if x is pi over 9, 3 times pi over 9 is going to be 3 pi over 9, or pi over 3, and the sine at that angle is equal to the square root of 3 over 2. Same will be true about any of those values in there. And that should match the answer that Pearson was wanting here, and it does. Gorgeous problem. Okay, hopefully that helped you out with this one. Let me know if you have any questions.